What you got?
I did.
That's pretty good. Hey, let's go.
How did you put really? Damn, not teach. Okay. Teach me how to be brutal. But still, it's pretty good.
You know, I see this.
我想再听到更多别的感觉。
Alex, where's your speed?
没事，到时候查录影也可以。查录影看的问题是录影那边是老师。不能我都写完再
我刚才发现原来他们要一句到底。啊，是吗？在上面写。
我去休息个5分钟，我回来马上。
不要管，录到底不是那个 stage 就好。我知道啊，反正我没来过。他们刚刚很多题目嘛，什么 relay disk。
8.2 I think that's
daily 不是，你现在在录吗？
哦，好。现在要录吗？现在
No need。
现在不用吧
But why？
啊？不用吧？
当然不用啊。
对吧
Let's start the last one of this fight. So, I still ask the opponent, please pick a problem to challenge the opponent.
tennis ball power.
Oh, we present tennis ball power.
What's that?
Present tennis ball power.
Red light disc.
Sorry,
Red light disc.
could you repeat like this?
Red light disc.
Okay, this. We will reject. Red light disc number 2. So reject. Yeah, we can reject. Okay, please pick another one.
Number one.
reject.
Yeah.
OK。
Drop exposure.
那个
Do you
他
have
们才
number?
Number。
Do you have number? We just talked about that topic.
Yeah, that one. Okay, suicide dice. Suicide dice.
Yes, we accept it.
Seven?
他是男曲，他的曲位是好的。Which one comes the name of他的真主语是17吧？也就和那个学位没有那么对他的学是蛮有还是第三个？第四个。然后第二个你对了。2.6。好像很难写。
Statement. To land a coin on its side is often associated with the idea of a rare occurrence. What should be the physical and geometric characteristics of a cylindrical die so that it has the same probability to land on its side and one of its faces. So from this, we identified the main properties. How should a cylindrical die be rolled to ensure randomness? What relevant parameters affect the landing of a cylindrical die? And how can we use these parameters to find the physical and geometric characteristics of a two-sided die? So to begin, I'll start off with the phenomenon investigation, and then I'll move on to the theoretical model, and then I'll move on to the experiment, and I'll conclude. So to begin, the shape of the die, it has a radius r and a height h, and we'll call the probability of it landing on this edge p of edge, where the edge represents the area between the two heads. And here's a video of us rolling. Here's a video of us rolling a die. So due to its depletion of energy from the inelastic collision of it and the surface on every bounce, it eventually must come to rest. And notice that in the beginning we dropped it with a ruler so that it has zero initial momentum, zero initial angular momentum, and it was at some height, and it lands on the face. And we did the exact same thing again at the same height as well, and it lands on the side as shown over here. Okay. So this shows that this three-sided die is a chaotic system. So when it is rolled from high enough, it has a large initial potential energy. So it's sensitive to its initial conditions, and it's a chaotic system. And that means that the rolling method, when the die is rolled from high enough, does not affect its landing. And moving on to the theoretical model, I'll begin with some assumptions. So to begin, we'll assume that the size of the die does not affect P of edge. So if we were to have the same die with the same height to radius proportions, except it would be like expanded larger, the P of edge would still be the same. We also assume that the dies are rigid, so that they do not attain wear or deformation when they bounce. We also assume the surface is rigid, uniform, and perfectly flat, so it's made out of the same material throughout. And also, we assume that air resistance is negligible because there is such a low force on the die. So a few geometric definitions. So we will call eta the ratio of the height to the diameter. We will call L half of the length of the diagonal of the die, which is equal to square root of r squared plus h over 2 squared. And we'll call beta the inverse tangent of eta, or the angle shown in the figure, which is formed by the diagonal and the radius of the die. So there are two types of falls where the dice hits the floor, right? An edge-inducive and a hedge-inducive fall. In an edge-inducive fall, the dice is more leaning to its edge for its height. And in a hedge-inducive fall on the right, it's more leaning to its head. And we'll call the probabilities of it landing on an edge-inducive and hedge-inducive fall PE and P of H respectively. Okay, and to figure out these values of P, we'll use like the circumscribing sphere of the cylinder. So if we were to choose a point on the sphere at random, this point could represent a hedge-inducive or an edge-inducive fall. So for example, we chose the point on top, right? And then that would correspond to a tangent plane as shown on the right image. And we can move that plane downwards to represent how the die would contact the floor. And as a result, it would be more leaning to its head when this point is chosen at the top. So it would be a head-inducive fall. And if we were to repeat the same process with this point, we would get that it's an edge-inducive fall. So to calculate P of E and P of H, we just need to figure out the area, like the middle area, the top area, and the bottom area. And to do so, we'll use the solid angle and stereo. So the solid angle essentially represents the amount on the surface of the sphere that is covered, and it's the 3D version of radians. It ranges from 0 to 4 pi in that the surface area of a unit sphere would be 4 pi. In the same way that for radians, the circumference of a circle would be 2 pi. And also we use spherical coordinates, which define any point in space using an r, which is the distance from the origin, a theta value, which is the angle formed with the azimuth, and phi, which is the angle formed with the x-axis. And to figure these out, we use the double integral to figure out the edge solid angle, so that middle area. And we defined it as the area described times the area coefficient dx, which is equal to sine theta d theta dt. And calculating that, we get that omega e, the edge solid angle, is equal to 4 pi sine theta. And as a result, the probability of the die landing on the edge would equal to 4 pi sine theta divided by 4 pi, the total amount of stir radiance of the sphere, which is equal to sine theta. And as a result, we can find P of H, the probability of a head-induced bounce, which is equal to 1 minus sine theta. So now that we know how a die can land, we can model its energy using gamma, which is the energy before divided by the energy after. The energy after divided by the energy before. And we assume that gamma is constant, so after every bounce, it would have an energy that's gamma times the energy before. So the energy after n bounces would be E of n, which is equal to the initial energy E0 times gamma to the power of n. And on a given bounce, a coin has a kinetic energy, we'll call that epsilon, and a well, m, about the center of mass. And we'll define the well as the amount of energy the coin needs to overcome in order to get to this middle state. And in this middle state, its diagonal is perpendicular to the floor. So as a result, it can go from an edge-induced bounce to a head-induced bounce, or a head-induced bounce to an edge-induced bounce after. And if it does not escape, then this is what happens. It sort of wobbles in place and never goes, it always stays in the same type of bounce. And as a result, if it fails to escape from an edge-induced bounce, it would land on the edge in the end. So calculating this well, this is a graph of the well to the angle to the surface, right? So if the die were to land on knowing its radius, right, it would be h over 2 above the ground. So it would have the maximum possible well to overcome. And if it were to land exactly on its diagonal, right, as shown over here, then it would have a well of 0 to overcome. And calculating the escape probability, we find it as if the kinetic energy is less than the well, right, then the coin can never escape because it can never overcome the well. But if it passes that well threshold, we'll say that it always escapes. And let f of e be the escape probability for an edge-induced bounce, and f of h be the escape probability for a head-induced bounce. And to calculate this, we essentially found the average of all possible, of all escape probabilities for a bounce on every point with this integral. And in the end, we get so, and then we get that if if the kinetic energy is greater than the maximum possible well, then the probability of escape on an edge-induced bounce would always be greater than 1. It would always be 1. But if the kinetic energy is less than the maximum possible well, then we can define, then the probability of escape on an edge-induced bounce is defined by this equation. And using the same process, we figured out f of h and almost the same results. So overall, the probability of escape on an edge-induced bounce is defined by the top equation, and the probability of escape on a head-induced bounce is defined by the bottom equation. and the probability of the probability of the coin landing on the edge, like coming to rest on the edge, on the icons, is defined by this probability. So the probability of the coin landing on the edge at all is equal to the sum of all those P edge lies. So in the end, we get that the probability that the coin lands on the edge at all is equal to the sum of all of these P edge lies. And moving on to the experiment. First, we calculated the coefficient of restitution by finding the initial and final potential final heights for 5 initial drop heights. And then gamma is equal to final height divided by initial height, and we got that to be around 0.64. And we used 5 different cylinders of radius 1.5 cm and height 1 cm, 1.5 cm, 2 cm, 3 cm, and 5 cm. And we got this graph with the blue representing the probability of edge and the orange representing the theory, and with error bars. So we got that so we got that the actual ratio of height to diameter differs for different values of gamma. So for example, in our one, we got the value is equal to 0.57. So in summary, we have a chaotic system, and relevant parameters are the height to diameter ratio and the coefficient of restitution. And the ideal characteristics, the ideal value of 8 of the tens of gamma.
Hold on, you can ask some question.
So let's say in your theoretical calculations, you try to assume, to ensure the cylinder dice randomness. Is that correct?
Sorry, what randomness?
Use like the way of assuming to ensure the cylinder dice randomness.
We calculated it with the equation. I'm sorry, I don't think I understand the question.
So is there any other ways to make sure that the potential state of the dice?
To make sure the potential state, what is potential state?
Oh, so you use a ruler to make sure the state of the dice, right? To make sure it doesn't spin or like have any angles, right?
Are you referring to
No, to the first, like, I guess it's the first.
phenomenon investigation?
You throw that.
Yes, we used the ruler and we dropped it down so that it would not exert any force on the tire.
So, but when you throw it down, can you make sure that the ruler doesn't flip and then flip into the coin and make some angles on it?
We just dropped it directly down. It doesn't have any force on it. If you force it,
So how about the friction? When you drop the rulers down, it might flip the coin, right?
yeah, but the friction would be so less that like it wouldn't really be much of.
Okay. So this topic is mainly about probabilities, right?
Yes.
So I can see that you made a lot of detailed calculations to get the ideal model of this dice, right?
Mm-hmm.
But
Oh, I'm sorry.
I'm only moving it down.
对对对，我刚刚这样子有时间到。我想不到。有什么？需要大概我这里就讲那个。
Today we're going to be opposing the three-sided dice topic. So first I want to talk about some pros from the previous presentation. So the pros that they did a lot of detailed calculations that is very detailed and it's specific. That's some pros of this presentation. And then, yeah, they use many ways to calculate the probability of the edges of this coin, so that to make sure the probability of this coin to land on each side and the edges are the same. Now let's talk about some cons. Since this is a topic is basically talking about probabilities, right? So I believe that in this topic we will need a massive amount of experiment, right? Because it's about probabilities. And the things about probabilities, you need a lot of experiment to make sure that maybe this dice, every probability of this dice to land on each side are equal. Like if you only throw like 10 times of this dice, it might not be accurate enough. And the second cons of their presentation is that I think they didn't consider enough variables, such as in their assuming there's no bounciness and no, right, they didn't flip the coin. They consider the coin just drop straightly from the air onto the ground and with no bounciness. So I believe if there can be more like variables that unexpected changes that cannot be calculated, their model could be more accurate and to more approach the real version of the three-side, equal chance to land on each side of three-side dice. The last is that the way when they're doing the experiment, their way to ensure the state of the dice maybe can be improved, since I think that simply using a ruler and just wish the friction is too small to flip the dice is not quite realistic. So the way we use to fix both this few problems, like lack of experiment, and to ensure the state of the dice can be, and how we ensure the state of the dice is that we simulated coins in programming environments. So after we calculated the model of the dice, we simply just enter those into a program, and inside the program we can ensure those dice are falling straight from the air onto the ground, and so that can ensure the state of our dice. And second is that because we use programming, we can do like thousands, tens of thousands dice at once, and to count like which sides they land on maybe some length at the side, first side, some length on the edges. So that will improve the problem of the length of experiment. Thank you.
So I want to talk more about my experiment. Sure. So in the experiment, we actually rolled the different dice, like hundreds of times on the floor from at least 1 meter high. So the initial rolling conditions, the initial rolling numbers, they didn't have any effect on how it lands in the end because it is so high up. And over here you can see the number of trials. As you can see, there are like over 100 for each of them. And then we use the 90% confidence interval using normal distribution to calculate these blue error bars. Also, the way we did our experiment, we didn't just drop it with a ruler. We actually just tossed it from that high. Like it wasn't it wasn't right. We spun it as well. I mean, the actual initial conditions, if we just drop it or if we just give it initial momentum, it doesn't matter at all on the final stage. It wasn't what we. It wasn't that video in the phenomenon investigation.
Okay. But how about the experiment? Like hundreds of times are quite not enough. We're talking about probability, right?
Yeah, but these are the 99% confidence intervals in the blue error bars.
And how do you make sure that the way we drop the dice will not affect the final results of which side it lands?
As I mentioned before, this is a chaotic system when it's dropped from high enough. So the initial, the actual landing of the dice is extremely sensitive to the initial conditions.
Okay. But I think if there's a way that we can ensure every dice drops the same way, then it can be more accurate, doesn't it?
Okay, but even at if you get it extremely accurate to a few decimal points, right? Due to the chaotic nature of it, it still will land on different outcomes. It still might sometimes land on head, it still might sometimes land on.
So maybe if some angles of your dropping it, it might make it land on one side easier. Wouldn't that happen?
Yes, but not when we drop it from that high.
Okay. Oh, is the mass of the dice even on when you're doing the experiment? Is the mass of the dice even?
Are you saying uniform density, right?
Yeah.
Yes, for the dice we had uniform density, but by our model, the density actually does not actually matter at all in determining the probability of it landing.
Wait, so you're telling, how do you make sure that it is equally separated, the mass?
Do you mean density is equal?
Yeah, the density.
Yeah, sorry, we printed these dice. They're 3D printed, and they're made out of the same material, PLA.
Okay. Okay. Yes. So now, can you show us the structure that you printed? Oh, the structure that you printed, the dice.
Structure, like we mean dice themselves. These are the dice themselves.
Hold on for a second, sorry.
Okay. Well,
Is the dice full of those structures, or is it empty from each?
it's uniform density. It's the exact same density. That's mass divided by volume at every point for these 3D printed dice.
How do you ensure that?
It's 3D printed. We use 3D printing to ensure this.
I want to ask if your dice it's printed in 3D print, right? So if it's structured by like how do you say that? Like a square, or is it you make out the outfit and then you fill the structure into the dice? Is it structured as like a
Printed layer
yeah,
by
I'll
layer.
draw it for you. So it's 3D printed, right? So I'm wondering if your dice is like made out of like small squares, versus like this. I mean, you know what I mean, right? With those 3D prints techniques, right? Or is it like you made out the outfit of this dice, and then you put your materials into the empty outfit of this dice?
I don't think that matters at all. In the end, it's still like uniform density, and even if it's not uniform density, our model still predicts like the same outcome for non-uniform density. Well, I have something to say about what you mentioned in your slide about how we didn't have enough variables to find like the correlation. Well, first thing, like the bounciness of the dice, it was the coefficient of restitution mentioned, I believe. Coefficient of restitution over here, which is like the ratio of like the energies before and after, which represents the bounciness, and also the other variables like the initial parameters, like as mentioned before by chaos, it's unable to find, impossible to find a correlation between them and the final ending.
Then the problem is that if you ignore so much variables, well then they combine together and becomes like a kind of like a bit effect to your experiment.
Well, the thing is, we only accounted for the important variables, like the geometry and the coefficient of restitution.
We're talking about like a fair three-sided dice in real life, right? But in real life, we cannot ignore those variables.
Oh, okay. You drop the three-sided dice onto a floor at like from extremely high, right? So no matter like if it has any angular momentum, or kinetic energy or anything, like those variables, like overall, because we dropped it from so high and it's a chaotic system, don't really.
Well, like the way we did simulate the falling drop of the dice at like program, it actually lands perfectly straight onto the ground since it's broken, right? So wouldn't that make this experiment more fair?
What would make the experiment more
Like falling straight, like the point falls straight, right?
Okay. But this is like the real world, and you can't make it like exactly fall straight onto the ground.
Yeah, that makes sense. Hold up, sorry. Did you ever consider using programming to do this experiment?
We used programming to like find the model, but we didn't use programming to we didn't program like the dice at all.
Yeah, just model the absolute look of it. That's all right.
Yeah, we didn't program. Oh, we didn't program like any videos of the dice or like that represent like it stayed at every position in time, right? But we did make a program using MATLAB to get this graph. This graph. We used MATLAB and our previous formula of the probability of it landing on the edge, as it's like a sum and it's like recursive defined.
You guys are really deep. I like that. Yeah. So I want to go back to like, how can we ensure that the different sizes, even though the how can you make sure like even the dice looks the same but it's getting bigger, it won't affect the probability of landing?
You mean like the proportions?
The proportion of dice is exactly the same, but it gets bigger. But would it affect the probability of landing on which side?
I think that's relatively intuitive. Like it would still be like the exact same motion as like the smaller dice, like a larger dice with the same proportion.
Okay. How about if it's based on different what we call it, structures or materials?
There's materials. So material of the dice and the material of the floor, the surface, those two together account for the coefficient of restitution, which we use over here. And yeah, that's how it affects the probability of the money on there.
Thank you.
I mean, to summarize. So, Tony, you want to summarize?
What was that?
Summarize.
Okay, so the opponent here wants to encourage our reporters, since they're the way they model this diet is super, let's say, detailed. Don't skip like if it were actually works that way in the real world. They have already considered so much variables and how it might work, and how they actually calculate it is super detailed, and I want to encourage that. But still, I think programming this, putting this topic into the programming environment might improve this experiment. Yeah, thanks.
So, viewers, okay, next.
Okay, so thank you for the presentation for both, and I appreciate it. And I want to ask you for a question. So you say that it's a chaotic system, but then what affects it? Particularly what thing will affect, like your expectations of the probability?
Like the initial, like the coefficient of restitution, the geometry of the dice. So the geometry of dice, that will affect the probability of land on edge, and the coefficient of restitution as shown by our equation over here.
Okay, then I will have a question for the opponent. And do you think that monitoring the experiment in the computer, like, will it really consider all of the parameters that existed in Earth? Or
Yes, you can set all those up.
But like, whatever if like there's unexpected things, like many things that would happen when you're doing the experiment. Then if you consider that, if you ignore it, or like you take it like uncounted, like by the monitor, like it's really extreme. So how will you define this?
So the way we define the program, we found that monitor that the environment of the program is like they consider all kinds of variables. So I don't think it will be a lot of difference from the environment to the real world.
Okay, and I have another question for the program. Like you mentioned in your experiment setup that you have a release with table. Then how did you choose the table, or how do you keep it like so, and like it won't affect the probability?
Actually, we did it on, I believe, the floor. Sorry. On this floor, we didn't do it on the table for our experiments for all the hundreds of trials. So actually, we couldn't really do that because it was a pretty large surface. So yeah, that might have contributed to the error.
Yeah, so there is another thing that if the floor isn't like flat enough, like if like in some sorts of environments, like the building is like a little that's ranged and where that you can't even feel it. So actually compared to the ground, it really affects the experiment, right?
Yes, but the thing is, our floor was pretty flat, and like the surface, it was the same material throughout.
Yeah.
So, like, it shouldn't have contributed that much in the end to the final probability of edge.
Okay, but the same material of the whole surface doesn't mean that, like, if you throw the side down, then it won't split in the other way, right?
Sorry.
The whole floor is the same surface, it's made of the same material. So, but you can't assure that if you flip a coin, then it will not like turn in another way. Like, it's not like if you like. How did you test the floor like it's exactly flat? Thank you.
So you're talking.
I don't know if it's in order if I want to go back to the previous question since I dumbly forget how to say the word. Is it in order? Is it in order if I want to go back to the previous question because I dumbly forget how to?
Okay, so I will start the presentation of our review to the three-sided dice and our team Tesla from Finland High School. Okay, so it's a problem statement, and I believe that you're clear enough, so I won't repeat it again. And it's a performance of the reporter, and the pros are they use theoretical models via literature, and they use many functions to try to prove like their models and everything. And they have great understanding of theories, like they use many functions and equations to prove their theories right. And they thought a lot of how to balance the equivalence between sides. But I believe that accounts are that failed to actually explain the use of the functions. They threw many equations and functions out, but they didn't say clearly how actually they used them. And so they mentioned a lot about theories, but not exactly how they calculate it. And they can do better in time management, like they didn't finish their report like just in time. And they failed to use physics site to explain methods, but they've used a lot of mathematical, but failed to physics site. And they failed to mention of their experimental data because of time management and of their explanations. And mathematics should focus on data statics instead of over-analyzing. But I think they do too much analysis on the model, but I believe that the most important thing is that you set up the model and you do more things about experiment and the statistics of mathematics. Okay, so here's the performance of the opponent, and the pros are they ask a lot of questions about like functions and how exactly and accurately they set up the models. And clearly pointed the problems of the report, like things they missed and the things they did not mention. And the cons are they took too much about unrelevant points of view, like for example, the mass of the coin. Like he made an example of whether it's full filled or it's empty inside. But I believe that full filled or empty inside, it doesn't matter because it seems the same. And they did not ask that many important questions. Okay, so I made some points that's missed by both of them and how to ensure the randomness. Like if we monitor it in a computer, then we can say that it's completely random. But what if we do the experiment like on the table or on the floor like the reporter did? And what size of dice will not hold to the expectation? Like for our experiment that I'm talking about before, like just a small hand that we mentioned in 3D and the 2D paragraph, and exactly different. And what materials will be the most ideal? Like they use 3D points. But we have to say that many other materials can be used to make the dice. For example, like wood or plastic or anything else. So it's 3D printing, like it's accurate, and they didn't mention about how they tried and tested the dices are actually expected. And here's a discussion topic of the minutes they spent. And the opponent, he gave questions about how to drop the dice will be the most ideal. And with the mass of the dice effect, the phenomenon and how is the dice constructed. And the reporter, how the height of throw will not affect it dramatically, and many other discussions. And by our point of view, and we considered models from 3D or 2D to assure the expectation. Like many things on the model, and I think it's not appropriate because I think we have to use the most easy and most understandable way to define this dice and make it more in statistics. And prefer probability on statistics rather than too much analysis on the model. Again, I believe this ends my presentation, and thank you for your attention.
So to begin, I'll talk about summary of our model, we use the fact that it is a chaotic system. The three-sided dice is a chaotic system, and that it has some contact probability and energy loss, and it has escape probabilities to figure out the final probability of it landing on the edge together with our clues. And we support this with the graphs of the coefficient of restitution and the probability of the coin landing on the edge versus the theoretical probability, which we used a 99% confidence interval to find pretty small errors. And we discussed whether it was possible to make it like a consistent experiment conditions, but because of like the chaotic motion of the dice, that is actually how to make how to ensure randomness of the die, because it is dropped from such a high initial potential energy. And the number of like variables, due to chaos, they can pretty much just be neglected. And even with a computer model, that can like make every initial condition, like it still cannot model chaos as shown like historically. Like it's impossible to use a computer model to measure chaos. And I think the data we used with our probability and the confidence interval was sufficient enough, like mathematically, and it does show like the correlation of theoretical model and the experimental data. Yeah. Thank you.
Okay, thank you. So, question from the jury. Thank you for the reporter. So you emphasize this question is this system is a chaotic motion. So how do you verify that? Because what's the criteria to call some system is a chaotic system?
So it is sensitive to initial conditions as shown in the slide where we dropped it from the same height with no velocity or angular velocity, and it did land on different ways. And also the degrees of freedom of our of the three-sided dice, like the velocity in x direction, velocity y direction, velocity z direction, and all of like angular motions, that's greater than 3 as well. So that also shows that it's chaotic.
Okay. Any other? I have some question. So the first thing is if I want to work out a fair three-sided dice, I believe in your ratio is the diameter to the height about 3 to 5 or something.
The height to diameter
The best,
ratio.
the best fair three-sided dice. So from your part.
I think we got in the end that we got around 0. And
At this.
so yeah, we got around 0.5.
So you make these dice. Okay, I want to ask, if you do, for example, if you do 500 times, how many show the top size, how many show the bottom size, and how many times show if you throw and fall down, that's the top of the system.
Sorry, the one.
Okay, if you have three-sided dice, okay, you can mark 1, 2, 3, okay? There is 3 states. Okay? How many times is 1, how many is 2?
So the two heads, those would be equal, and we figure out the probability of edge in the equation over here, and this would figure out.
I mean just do the experiment so from the result. Have you done that?
The experiment
From the results. If you for 3 times, 300 times, 300, 700, 81 for this phase 1, phase 2, and phase 3, how many times?
So we counted that in our experiment. So we don't have the exact number of times it lands on the edge or the base, but like these are the proportions. Yeah.
Okay. 现在 reporter say it's the ratio is the wrong. Opponent, do you believe that?
Excuse me.
Do you believe the ratio between the diameter and the height is the fair suicide?
Oh, I mean, if they can give me more specific, like they model it out, right?
Do you agree or not?
For now, no.
Yeah. No.
Yeah.
So what's your best ratio?
I believe, I'm not saying that I think you're wrong. I'm just saying they can give an improvement through experiment.
Do you have one? No.
Yes, we simulated in.
What's the best ratio you have?
What?
The diameter and height, the ratio. So you can get the fair size.
I believe it's.
That's fine.
I kind of forget the specific.
So you believe it?
So I don't actually, because I don't actually believe that, because I think I need more like information from the reporter, and like from our own experiment, we calculated like root 3 and root 2, and like we use binomial distribution to prove all of them are wrong, and we do the 7/3 and also 2, and we believe that the best ratio is 2.
Why there exists and fail three-side dice? Do you have the reason to explain that?
Do you mean, sorry,
Why you believe that there exists a fair three-side dice?
well, actually, we got that the fair three-sided dice, it depends on the coefficient of restitution. So we can't make a three-sided dice that would like land the same probabilities on like any surface. There is a three-sided dice for exactly one surface.
Similar question. Whether there exists fair five-side dice? Can you guess?
Five-sided dice, but it depends on the shape of it though. Like, what would the shape of the dice be?
Well, anyone you can imagine. Five-sided fail, five-sided dice.
For example, like a three-sided dice, I can just make a cube, except for like 2 spaces, I make that 1. Another 2 spaces, I make that 2. Another 2 spaces.
You can have a cube, three-sided and the up and the down. That's a five-sided dice. So, whether there exists such one? Yeah, just one. Just for fun. And then you have you have any reason to believe there exists a fair three-sided dice?
Actually, after all this experiment we did, I kind of go to like, I don't think there will actually be a fair three-sided dice, but I think we can get a limit from, it could appear in, we got 2 proportions of the dice. So for the first proportions, we got 2 less of the, 2 less for the land on the edges. And can I finish? Sorry.
You can finish it.
So, and for the second proportion, it lands too much on the edge. So we believe that maybe the fair three-sided dice exist between these 2 proportions, but I failed to calculate them out. So I kind of go to like, it may exist, but we cannot figure it out we can model it out. Yeah, we can only guess it's kind of maybe between you.
Your opinion?
So I believe that there is a true three-sided dice, but I think the most important thing for us is to know about the range, like how about the range, like about like our expectations of each side is like 333 if we close it for 1,000 times. And I think like we have to calculate the range, like for example, what I just said, like for between 2 and 7/3. And for example, like inside the range that we can accept it is not too far over expectations, and that's what I think is most important.
Thank you.
Okay. I think we go to the point.
这样 rarely 得做的比较好，因为这样一直压下去，就本来就有东西出来。
他没有说，他没有说，
他顺便没有说他
真的是
多少次啊？那我会先把它弄掉。
Let's start from the program to join the racing grade. 5, 8, 6, 7, 7. Then component. 5, 6, 4, 5, 7. Then reviewer. 6, 7, 5, 8, 7. 8. Thank you. I need to make some statements because I gave the lower grade for the component. I think the problem should be, at least you should show some experiment now. Okay? The easy way is do the experiment. How many sides for the half of button? Then you change your shape. Okay. So I don't believe, at least I don't quite believe that this can just do some simulation. So you can get the fair side. Okay, so that I did not give you very time to do. The AI one, to make some comments.
For the reporter, I think the integration for the solid angle maybe consider density of state, because it just integrate the space. It don't consider the shape. You understand? Because you just integrate the solid angle, right?
Yeah. We integrate.
So you have to consider the center of mass or something, or top or something. Or yeah, I think you miss the density of state for this.
Okay. Any other two? No? Okay. Okay. Thank you everyone.